Yeah, good morning. In this session, I would like to demonstrate drying of solid materials. As you can see, this problem has been taken from this reference. 2000 kg per hour of dolomite, moisture content of 20% at 95 degrees centigrade is to be dried in a counter current dryer. So the dryer length, the residence time are provided. You are required to calculate the solid moisture content at the exit. If you are using air with an initial temperature of 200 degrees centigrade and a flow rate of 10,000 kg per hour. And the mass fraction of water in inlet air is about 0.002. And you are required to calculate the temperature and moisture content profiles of both solid and gas phases. So you are given with some data, convective mass transfer coefficient, drying curve and PhD. This data is given along with the critical moisture content and equilibrium moisture content. So the drying curve data is provided here. The particle size distribution is also provided here. Now remember, in this problem, we are dealing with two solids, CaCO3 and MgCO3. They are actually conventional inert solids, right? So we should be able to even handle them as conventional components because we are able to represent them by means of molecular formula, and we don't have any chemical reactions happening. So we should be able to handle them as conventional inert solids. So let us try to see how to simulate this problem. So we are using air, and then we have water because air is containing some amount of water as well as wet solid, and the two solid components are CaCO3. Let us say I declare this as a solid, and then MgCO3. This is also a solid material. So these are the components we are going to handle in this problem. Now go to the next input step. Choose a property model ideal. To the next input step, simulation environment. Now create your simulation. So you can see various models under this head solids, and some equipment for solid separators models are also available. So if you go to this, you will be able to identify this dryer. So select this model and then connect input and output. So be aware that this has to be the inlet gas stream, and this is the outlet gas stream, and this is your wet solid followed by dry solid. So let us rename them. This is air in, inlet air, and this is your outlet air. And this is your wet solid. And this is your dried solid. Now, because we had some solids, now let us go to the stream class. So you can select mixed streams, CI solid streams. Okay. So I have selected this stream class. Go to the next input step. We were given this is with respect to air in. It is at 200 degrees centigrade. Let us assume 1 bar. And the mass flow rate of this air is given as 10,000 kg per hour. And the mass fraction of air is given as, you have some 0.002, 0.2, this is 0.002. The mass fraction of water in inlet air is 0.002, about 2%. So let us give that data, 0.002, and the remaining is obviously 8.998. Remember, both these components are conventional. Anyway, in the air, there are no solids present. So we can go ahead. Now we need to define the solid, wet solid, which is coming at a temperature of 95 degrees centigrade and 1 bar. And we have 2000 kg per hour of this wet solid is coming. One way of dealing with, remember, we have 20% water and the remaining is CaCO3 and MgCO3. So out of 2000 kg, 20% corresponds to 400 kg per hour of water, and the remaining has to be CaCO3 and MgCO3, equimolar contents. So let me go into the Ci solid stream. So 95 degrees centigrade, 1 bar, and the composition is, the mole flow rate, mass flows are 400 kg, 800 kg, because 40% CaCO3 and 40% MgCO3, 20% water. Water was accommodated in the mixed substream, this being a conventional compound, and the Ci solids, CaCO3 and MgCO3 were accounted in Ci solid substrate. So we have defined this stream, both the input streams. Now we need to talk about the block. So it's a continuous dryer. We had 1 bar. The details we are given with. Co-current dryer. The dryer length is dryer type we can select. Convective dryer. So instead of volume, we were given with the residence time. So the length of the dryer is given to be 6 meters. The residence time is given to be 3 hours. Right? Now the mass and heat transfer. Now you are given with the convective mass transfer coefficient as 5 into 10 power minus 4. So let us select that mass transfer, specify mass transfer coefficient. So meters per second, it is given in terms of meters per second, 5 into 10 power minus 4, 5e minus 4. So this we have given, and we need to talk about, sorry, I think we made a mistake because the PSC is also given. So just 1 second. I'll go back to stream class. Because we are having PSD distribution. So this is going to include mixed conventional compounds, conventional inerts with PSD. So flow sheet, that is the next. So drying curve, critical solids moisture content is given as 0.1 on a dry basis, and equilibrium solids moisture content is given as 0.05. This data is available in your so normalized drying curve function. This is data. So you can we don't have a function, but the data is given to you in your problem statement. So the normalized solid moistures 0, and the normalized drying rate is 0. Please refer to the problem statement. 0.1, 0.1, 0.2, 0.5, and 0.35, 0.8, and then we have 0.65, 0.9, 0.85, 0.95, 1 and 1. So this is what I was referring to, the drying data which has been provided here. In the same way, we need to provide now the particle size distribution. Okay. So this will be available in the wet solid. This we need to go into this. We have changed the data, that's why the previous data, we have changed the stream class, so that's why this is gone. 25 degrees centigrade, 1 bar, and we know the mass flow of both these components, 800 and 800. Now, because we have taken this as PSD, stream substream, now it is asking for particle size distribution. Now, how many we have? So we have this data available, 1, 2, 3, 4, 4 intervals. So let me reduce this. Number of intervals are only 4. Okay, and then the data is given in terms of millimeters, and size in mm is lower is from 4 to 5 mm, then 5 to 6, then 6 to 8, 8 to 10. This is the range. Okay, close. Now, according to this range, the weight fractions are given 20%, 0.2, 0.2, 0.4, 0.2. You can once again refer back to the table that we had for the particle size distribution. So you can see the same data is entered. Okay. So having done this, I think we have completed all the required input. So we should be able to run the problem. We got to our results. Now you can probably see individual results are the total stream summary. So let us look at mass flows. 10,000 kg per hour of air is entering, 20%, sorry, 2% is water, so we have 20 kg, but the exit is containing more amount of water. Air remains as it is. It's a tie component. So 400, roughly about 402 kgs of water has been picked up from the solid material, from the wet solid material. So finally, we have dry solid at 6803. So many kgs of dry solid. This is the amount of wet solid. If you are looking at mass fractions, now this is what we are required to calculate the quantities and the composition. So we have so with these conditions, we were able to remove only small fraction. So this is water. What was the amount of water we have? This is water. From 81.8%, we came down to 80.9. The amount of water removed is not that much, but these are the compositions. Of course, you should be able to see. Now, I would like to go into this results, and we should be able to identify whatever data you want, and we can also look at various profiles, either from here or maybe here. So how the solid temperature is changing. Remember, the solid is entering at 95. By the time it leaves the dryer, it is around 73. Similarly, you can see what is the vapor temperature. Vapor is nothing but air. Air is entering at around 200 degrees centigrade. Was it 200? And yeah, this was entering at 200. But by the time it comes out, it is 173. So like this, you can observe what is happening to various profiles. How the vapor moisture is changing, how the solid moisture is changing. So this is how the moisture content is changing with respect to the vapor. And similarly, you can also see what is and how the solid moisture is changing. Right? So we were able to calculate whatever is required as per the problem statement. So this is how you should be able to model dryers. Remember, in this case, we were not required to decompose the solids into its constituent elements, because essentially we are dealing with only conventional inert solids, which we were able to handle in most of these unit operations. So with this, I would like to close the session.